So our last speaker for this session is Xingfeng from Zhejiang University. So he has a very broad research interest in the AI and IoT security, with the focus on the security and privacy, specifically on the multimodal intelligence systems and their impacts on users. And he's actually a final year PhD, and he's actively looking for academic opportunities on the job market, and especially something like a postdoc. So today he is going to talk about a new attack, and then for this specific attack, I guess it's going to be an improvement over various prior works in this domain, including Dolphin attack from the same group, which actually won a CCS best paper. And let's see how they were able to improve even on that, and then by considering the user aspects.
Thank you.
Okay, Xingfeng, please.
Okay, thank you for your introduction. Yeah. Hello, everyone. My name is Xingfeng. I am from the USS Lab, Zhejiang University. I am going to introduce our work in audible adversarial perturbation, manipulating the recognition of user speech in real time. Automatic speech recognition systems are everywhere. They are deployed in the Siri, Azure, or Amazon Echo, and make our lives easier. And they can listen to users' command and recognize or execute it. For instance, even open a door. However, ASR systems have been shown to be vulnerable to the adversarial examples. Audio adversarial examples are crafted by adding the small perturbations onto a benign speech sample, which does not impact human comprehension, while it can spoof the ASR models to output incorrectly. So in this work, we want to explore what properties should the ideal AE attacks possess. First, the attack must be stealthy to avoid alerting users or perceived by the users. So it should attack when the users are speaking to the ASR system and in an inaudible manner. Because in such case, the system's reaction like LED blink or vocal prompt are expected by the users. Otherwise, if the user is not present or there is zero user input, such reaction is spontaneous and will raise users' suspicions. Second, an ideal attack must be universal to alter any user speech into adversary desired command, no matter what content the users will speak. And third, the attack must be practical to maintain effective even after long-range delivery, because the attack device cannot always be deployed physically close to the victim ASR system, especially when the user present scenario. Unfortunately, existing AE attacks cannot meet the wish list, although they focus on limiting their adversarial perturbations very small or hiding them into the innocent sounds like music, noise, or ambient sound. However, they are still in the user's audible band, and users can notice such suspicious sound. Moreover, this constraint also limits audible band AE attacks universality and practicality. Thus, a single perturbation is too weak to tamper with any user speech, and their attack is limited in a short range. So, can the attack be entirely inaudible yet universal and practical? In this work, we present VRIFLE, and its basic idea is to achieve completely inaudible attack delivery by modulating the adversarial perturbation onto ultrasound. So how can VRIFLE achieve inaudible? We employ the amplitude modulation to load our generated perturbation onto the ultrasound, so it's inherently inaudible during the over-the-air propagation and will be received by the microphone deployed in the ASR systems. Then, the inherent nonlinear effect of microphone sensors make the high-frequency signal demodulated to the low frequency, and will bypass the filter in the microphone circuit just like the normal audio signal does. So in this way, the adversarial perturbation can successfully get into the ASR systems and manipulate its output. Since VRIFLE is inaudible by design, it's no longer limited by the stealthiness constraints like prior works, and our perturbation can have large amplitude and unconstrained length, as the picture shows. And with such a broad optimization space, VRIFLE is highly universal to tamper with any user speech, just like, for example, open the door, and regardless of what the content the users will speak. Moreover, as VRIFLE is inaudible by increasing the emission power, we can even achieve very practical long-range attack even at 10 meters away from the victim device. So we can see the potential of turning to a new AE paradigm with completely inaudible yet universal and practical attacks. To implement VRIFLE, we still need to address 3 key challenges. The first challenge is a long-standing problem that AEs work well in the digital domain yet lose effectiveness in the physical domain. This is due to the digital and physical domain gap, which can lead to the signal distortion and deformation. The second challenge is, although VRIFLE is universal, a given perturbation cannot tamper with excessively long user speech. And the third challenge is, traditional double sideband modulation carries a wide frequency range, while the sound leakage will occur in an unspecialized device like everyday life loudspeakers, which are designed to deliver a low-frequency sound instead of the ultrasound. So how can we address these challenges and realize VRIFLE? For the perturbation distortion challenge, there are 2 mainstream methods. The room impulse response have been widely applied for audible band AEs, but they cannot estimate AEs delivered via ultrasound. And the end-to-end machine learning-based modeling requires too much paired data for various attack distances and varying the injection angles, so it's hard to enable location-free attacks. Specifically, we model the ultrasonic transformation to well estimate our perturbation for its received version in the victim device ASR systems. First, we have the baseband perturbation, which will go through a series of complex transformation. Then we justify that this transformation actually approximates the baseband audio, goes through a transformation function HF, and add on the ultrasonic induced channel noise N. So the estimated audio M hat is almost identical to the ground truth recorded M delta, showing our effectiveness of the ultrasonic transformation modeling. So how to formalize the HF transformation function? We first generate a 10-second sine sweep and use the target device's microphone to record such sine sweep signal. And then we can derive linear and nonlinear components related to the baseband transformation by deconvolution operations. Finally, the ultrasound frequency response can be obtained by summing up all of these separate components. The above steps demonstrate how to describe the perturbations transformation in a specific location to enable successful attacks at various perturbations. Attackers can collect the UFR and channel noise samples by varying the attack positions. Thus, the UFR pool and noise pool are formed. So how can we involve this into our optimization pipeline? In this way, we can mimic the signal received at the device side in the digital domain optimization. During each iteration, VRIFLE randomly chooses the UFR and the noise samples from their pools, and then the perturbation will be encouraged to manipulate any user speech, and their mixed signal are recognized as the adversary's desired command. With this optimization pipeline, we can finally obtain a single robust perturbation that enables location-free attacks. For the unpredictable user speech challenge, we propose an alter and mute strategy, where a universal perturbation first alter part of user speech into attacker's target command, and the linked silence perturbation will mute all user speech into blank. We first create the silence perturbation. Its training pipeline involves randomly shifting the user speech and randomly selecting different speech samples. Thus, the single perturbation can tamper with all speech samples into blank output in a synchronization and content-agnostic manner. Then, similarly, for the universal perturbation, we can see that the delta is linked with a well-trained silence perturbation chi, and it can alter and mute any speech, thus achieve a highly universal ASRs manipulation. In addition, we also consider the variable relative loudness of user speech and the adversarial perturbation, and users may live in rooms with different sizes and shapes, so their voice can go through varying attenuations and reflections. We incorporate all of these factors into our optimization pipeline. For the sound leakage challenge, we employ upper sideband modulation, which saves the energy by removing the lower sideband and benefit long-range delivery of our perturbation. In this way, attackers can deploy the ultrasonic transmitter very hiddenly and deliver long-distance adversarial attack. And we also implement a portable attack device. In this way, attackers don't have to deploy the equipment in advance, and it's highly stealthy. We also demonstrate attack with everyday life loudspeaker is feasible, forming a comprehensive attack strategy. In line with prior works that targets deep speech to ASR model, we test how much user speech can be manipulated by our VRIFLE. We select 10 representative malicious intent from the view of attacker, then we evaluate VRIFLE's digital and physical domain performance. We first investigate the impact of epsilon constraints on VRIFLE's universality. Results demonstrate that a larger epsilon can create a more universal attack. Specifically, a silence perturbation can mute more than 27,000 user speech, and a single universal perturbation can alter almost 19,000 user speech into open the door. To evaluate the impact of different target commands, we select 10 typical malicious commands, and we observe a consistently high success rates and low character error rates across these 10 commands. We also investigate the effectiveness of our ultrasonic transformation modeling. We set 4 groups. The first group is direct ultrasound-based attacks, namely the dolphin attack, which emits a voice command, open the door, and VRIFLE attack without considering the physical and digital domain gap, namely using the UTM. And another control group use a low-pass filter to approximate the function of our UTM. The experimental results demonstrate all control groups are ineffective, and our ultrasonic transformation modeling is vital for realizing physically effective inaudible adversarial perturbations. We also find that VRIFLE can maintain effective even attack at 10 meters away from the victim device, and it also supports wide injection angle attacks. As for the resistance to defense, we observe that quantization, VAD, and OPUS compression are ineffective. Although bandpass filter and downsampling are effective against naive adversary, but they can be neutralized by our adaptive adversary. Finally, we gave 3 takeaway messages. First, VRIFLE reveals a new attack surface of audio adversarial examples which may generalize to audio backdoor attacks in a completely inaudible manner, simultaneously enhancing the universality, stealthiness, and attack distance. We make the first attempt to present the ultrasonic transformation modeling. This method may transfer to laser or electromagnetic-based inaudible AE attacks. And VRIFLE extends prior AE attacks to the critical user present scenarios with real-time manipulation of any user speech into adversary desired commands. Our demo and source code are available. Thanks for listening, and I am more than happy to take questions.
Questions?
Ryan Gertis again from Virginia Tech. Could you explain the differences between your attack and the Ghost Talk attack of over a decade ago, aside from the fact that Ghost Talk uses electromagnetic waves and you use acoustic waves? Because the same thing is happening, the same modulation to bring it down to the targeted frequency is being used.
Okay, first of all, our threat model is we should attack when the user is speaking, instead of we just assume there is no one speaking. I think the prior works like Ghost Talk, Dolphin attacks, they will, as the ASR systems always respond with voice command in terms of LED blink or vocal prompt once they receiving such commands. So the Ghost Talk or Dolphin attacks and prior AE attacks, they can work well in such scenarios if there is no user speaking, right? But they will alert users because in the user present scenario, that's our threat model. In such scenario, users will be alerted by such spontaneous reaction of ASR systems, a spontaneous LED blink. Okay, I think, but it may. Sorry for my absence knowledge of the Ghost Talk, but I guess it may be limited by the attack range, right? Because it should overpower the user speech, right?
Well, I mean that's just a question of how much amplifier you have.
How much amplifier?
Yes,
the attack power, you mean?
Yes, exactly.
You can see the detail of our paper. It's around 3 watt.
Oh, I meant the Ghost Talk attack. I mean, you can extend that to several meters if you want.
Several meters. Yes. Oh, you mean Ghost Talk can attack from several meters? Cool. Okay.
So let me answer the question.
I was hoping you would.
So the difference is actually we're looking at different vulnerabilities. With Ghost Talk, we're looking at conductor as the attack surface and getting into the system. And it's purely doing like, we call it masking kind of thing. I'm more powerful, so I can overwhelm whatever you are talking about. And now in this work, it's looking at both the sensor vulnerability and the model vulnerability. So you're combining both, and you're using kind of the model will misunderstand things, and at the same time, the sensor interface is slightly different.
It's like an adversarial example with Ghost Talk.
Right, yes, you got it.
Okay, thank you for your question.
Any other questions? Maybe Takashi? Yeah.
Takeshi Sugawara from UEC, and thank you very much for the great talk. And can you please explain a little bit more about the stealthiness you are targeting? Because after a successful attack, the smart speaker will respond to the legitimate user with something not requested, and the legitimate user will, notice that. And why that is not the problem regarding stealthiness?
If I understand right, you mean if we attack when the user is speaking, they will still notice such unwanted result, right?
Yeah, right.
Okay. Actually, I don't present such details in our main slides, but we provide a very stealthy attack strategy in our users by the means of user study in our papers. Around it's located in the page 17. You may see more details about this. Thank you.
Okay, so users just ignore that.
No, we don't ignore that. I can simply explain that. We just use man-in-the-middle attack. For example, you can first utter the user's command, and then you use an additional microphone to record the user's command, and then replay it in an ultrasonic attack way. Yeah, so the user's command will be satisfied. Yeah.
Yeah, I was also trying to ask about the user study, but then page 17. Yeah, I guess we all remember.
Yeah, thank you.
Yeah, I guess this concludes this session. And then for those who are faculty, need funding, so the NSF office hour is ongoing, so definitely go there. For other people, there's a birds of a feather session, so yeah, enjoy, everyone.